This video is being sponsored by 𝗣𝗥𝗢𝗣𝗪, which has a collection of well-written crafted courses for software developers, from Python to front-end to system design to scalability to Docker and whatnot. Learning at 𝗣𝗥𝗢𝗣𝗪 is really powerful because they have all coding workspaces in the browser itself, and also they offer 𝗣𝗥𝗢𝗣𝗪 Unlimited, in which you pay only once for all the courses. They have annual and monthly plans, and my audience gets a 10% additional discount on the 40% campaign they have for India. So you get a 46% discount on using the coupon Rachit, and you can have the link in the description below. Hey everyone, this is me Rachit. Welcome to yet another video in our system design series where we pick topics of system design one by one and deep dive into them. Today's video is going to be very much interesting because even professional developers with experience are not generally aware about what are the data structures behind databases. And this is something which can give you really a surprise when it comes to a system design interview. And this is exactly what we are going to do today. We are going to understand what it takes to design a database ourselves. And typically there are two types of storage engines. One is log structured based, other ones are page oriented based, which are based on B trees. We'll come to the second part later. Today we want to do something easy, but we will see how much of designing it takes to design something as simple as a simple key value storage. So these are the requirements. Once you have the question, the next part is to clear requirements with the interviewer. And over here, since these are some things which you do not do generally as a software developer, it's better if you pick something easy and make it even more soundproof. So this is what I would recommend. If this is the question, you should start with the requirements in the sense that, okay, so we have to support key value storage. And let's say there is low latency per write as well as read, right? And if you have a good amount of experience, probably 2 or 3 years at that point of time, it's also good to also mention that we also want to focus on the ease of recovery and durability when we are designing this database. What this means is once the server crashes, it should be easy to restart it with the correct data with the last snapshot. And durability means that if you are saying that something has been written, it should be read correct with the correct value when you do subsequent reads. So these are the basic requirements, and after that you would first want to write down how things are going to look like. The API can be something like as simple as there is a dbWrite command which takes the key and value. So over here it would be good if you store values as strings. It makes your life a bit easier, and if you have objects you can stringify them in JSON, and then you can simply store them as this. dbWrite takes key and the value. Again, if you want to write for some different key, you can do it in this fashion. And if you want to read, obviously the API should only take the key and then it should just give the value. So if you do something like this, generally what we can think, like what would be the simplest approach for you to support something like this if you're talking in terms of database? Well, you can write these key value pairs in a file in such fashion. You can append new entries like this, and for user A the value is this, user B the value is this, right? And there is no header file because CSV with no header file is something that only has a certain fan following, if you know what I mean. So this is what it looks like. Very simple, but it does the work. Even if you write, even if you start the process again, since we have written to disk, this is a file, demo.db is the name. Since we are writing to disk, it is having persistence. So even if your server crashes and you start again, your file is there, you can again read this file and start doing the reads, right? Very simple and very easy thing. Let's now understand what happens. Now let's go through some workflows, what's happening behind the scenes, right? So let's see that there is some user who wants to write this key user 7 and the value is 17. It can be the bank balance, right? And obviously this is not the user who will just say that this is my balance, but let's say the input is key is user 7 and the value is $17 that we want to write. So over here we can see that in our DB file, which is simple as key value pairs thing in every line, we go to the user 7 entry, and over here we have appended 17 in the balance, right? Very simple, very easy. But let's now discuss few scenarios, and this is something that we should do in general, like any system design rounds. Go through the workflows and at that point of time discuss other scenarios that you have to consider while designing something. Well, a normal question at this point, which is still not clear, is what will happen if you already have a user with data about it. So if user Y5 had a balance of 71 and it was already returned to a database, what happens now if there is an update on the balance of user 5? Do you do an overwrite? Do you replace this 71 with 100? Or do you append a new entry for user 5 and 100? So this is something that we had not talked about, but it is something that we might miss during designing anything. But these things are important, and it tells you that the candidate is well aware about designing foolproof solutions and they can think of corner cases and scenarios which need to be handled. So at this point, there are two ways. We can have an override strategy or we can have an append strategy, right? Now, if you talk about override strategy, what are some things that you can think about? Well, you can say that keys will always be unique. However, in case of append strategy, we can say that keys can duplicate and the last entry will always give us the latest information, correct? Over here for user 5, 71 is the old information and 100 is the latest information. So obviously, since we are duplicating keys, it will take more disk space, but the override strategy is going to take less disk space. Also, reads can stop at the first key found because there will only be one key found, and reads will be for the last key matter. So you can also do a reverse read for the file in this append strategy, and again you can stop at the first key found. But writes are slow. Why? Because you will need to scan the entire file. You need to figure out where is the key for which you want to update the data, or whether you have to append a new entry if the key was not there in the database. But in this case, append strategy, it's very easy. I simply have to append and it's super fast. There is no scanning of file, only just go to the end of file and just dump it. The update logic obviously makes the code tough, right? And over here in append strategy, the code is very straightforward. So these are few things that we have discussed. And if you want to talk about a bit advanced things, we can say that the file, since the database is updating things, it's kind of a mutable data that we are looking at. However, in append strategy, it's always based on immutability, and we will see how this is going to be super helpful to us. Also, if there are crashes, it might happen that there is a partial of old and partial of new entry in the value. But in this case, it's not like that. And also, to do sequential writes on magnetic spin hard disks is super fast. In this case, you will be writing to different values. Over here, you are always doing writes sequentially. You are always writing in the continuous disk space. So if this is the file, since appending are always happening in the subsequent bytes, these are sequential writes which give us a better performance. And databases are all about having the correct disk access patterns to do optimizing of the writes. So that's why very much preferred, and append only strategy is something which is very common when you're talking about log structured storage engines. However, we have seen that the reads are slow in both cases, right? For reads, you still have to scan the whole file, which are having order n worst case, and this is something that we need to solve because this is one of the requirements. We want real fast writes and real fast reads. This is a requirement. So how can we take the current approach of append only strategy and also ensure that the reads are super fast? So obviously indexes is something that comes to your mind. For relational databases, indexes are something which take additional hard disk space, right? Also more RAM. And what they do is generally they have an overhead, but they give us a really good optimization in the reads. So indexes are something which comes to our mind, and this is exactly what we are going to do. They do have an overhead on write, we will discuss that, but they do provide better performance in terms of read. So in our case, it's very easy. Obviously, the key needs to be in the part of index, and I will quickly demonstrate what do I mean by an index. So index, I'm going to store it in memory as a cache, and I'm having a key, and I'm storing the byte offset in the disk about every key. So what do I mean by that? This looks confusing. It's not. Let me explain that. So if you will see, user 1, the offset is 20. And what are these things? Well, this was your file. User 3 is at 0 byte, for example. Obviously, it can start with some 310 or something random, but let's say the byte offset for, so this is the file, right? I'm not talking something in memory. This is the disk that we are talking about. And these are the byte offsets in the disk at which we can find the data written. So for user 3, the byte offset is 0. For user 1, it would be something like 20, and so on and so on forth. Now what I'm saying is, once we have these bytes offset and these keys stored in this RAM, in memory, this is going to give us a real boost to our reads. Why? Because reads after indexing, you need to demonstrate to the interviewer in this fashion that, okay, let's say the user wants to read for user 7. If they do want to do that, well, we go to our RAM, we go to this cache which is there in memory. We see that for key user 7, the byte offset is 90. We traverse it all the way to the disk. We find that at disk offset 90, we do one seek in the file. We directly reach here. We do not scan these entries. Everything is saved. We directly reach here and we read this value and we return 70. Super fast, right? Again, at this point of time, it would be good if you do also discuss what happens if there is a write scenario, right? So in write, what you do is, if you want to do a write for user 5 and it was already an entry over here, so this means that, let's say the byte offset over here was 50, I'm just assuming, and over here it was stored as user 550. But now if there is a new append, a new update on user 5, it would go to the end of file and that byte could be 120. So you update this from 50 to 120. You need to do this overhead. You need to update you need to maintain the correctness of this key and offset pairs. So that's why there is an overhead on write, but definitely a greater performance on read. So if you talk about things like this, it looks like you're going on the right path. And again, there are so many things the interviewer can talk about at this point of time. Also, we can go into the low level design, which we will actually do, because I just want to show you that what are the benchmark performance for both these strategies. So let me just zoom into this and I will quickly go through this. So I did a benchmarking test for 10,000 entries, and this is for brute force, in which we did not have any strategy to optimize reads. In that case, for 10,000 entries, it took us 1.74 seconds to write these. However, the reads, they took 91.29 seconds, super long for 10,000 entries. And after we created this index strategy, there was an overhead on write. Same 10,000 entries now take 1.88 seconds to write, a little bit of, you can say, 0.1 seconds more, right, for 10,000 entries. However, think about this 0.7 and 91. The reads have been super fast now. And also, if you'll notice, there is only one disk IO, right? And that can also be avoided in some cases if the file system is having a good cache strategy, right? If you are going to again read again and again the byte data written at 90 offset, if the file system is also having cache, the next time it can directly return the value 70. Super great. So we have seen that we have made few decisions, we have made some trade-offs, and we have reached at this point in which we have optimized the reads, we have optimized the writes, and everything is looking great. But as a designer, you need to be aware about what are the things which you will still handle and what are the things you definitely can't support right now. So at this point of time, what do you think are the next things that we should look into? Well, since we took the append-only strategy, there is too much of disk space that we are consuming. Let's say that on average 50 transactions are existing per user. So since we are doing append-only strategy, it means we will take 50 times extra storage, which is something which is definitely not good. How can we solve this? Well, there is something that you can do, right? One thing is that you can definitely have only one active file at which you will read, and as soon as the file reaches 100 MB, you split it and that chunk is saved. It's obviously read only. There are no updates done to the chunks once you split them, because there is only one file at which you write. So the DB writes continue to happen at the active file. Right now it's 25 MB. Once it reaches a certain size, you can just stop writing to that, create a chunk and start writing to something new. How is this helping? Well, before we go into that, the idea is basically to have small chunks so that we can remove them a bit later. So basically, if the chunk has, let's say, some keys, and for all those keys there are some entries available in other chunks or the active file, then that chunk is useless. That's the idea, that we can remove certain 100 MB chunks later on. This will give us free disk space. But before we go into that, how will writes happen now? Because it might happen that for some key, the value only exists in one of the chunks and there was no update for that in other chunks or active file. So let's demonstrate that also. For DB reads, every chunk is having their own hash map, which provides us the better performance and very fast lookup about whether the key is present or not. So in the active file hash map, if we find the key for which we have to perform the read, well, very best scenario, we simply do the read and we return the value. Otherwise, we go to the next chunk, we perform a lookup in the hash map of this chunk. If we find, we return, otherwise, so on and so forth. So obviously things are working, nothing has broken, right? But there can be another thing. Since these are only read only, no modification is happening on these chunks. It should be modification, sorry about the pronunciation. So there can be a background thread which can work on these chunks. That's the step one. It will take two chunks, for example, or it can take multiple. It will compact them, create a new chunk, and then the reads, if you will look, the reads can now be served using chunk 3 and we can get rid of this. That's the idea. This is how we are freeing the space. So let's say there were duplicate keys present because there were 50 updates we are looking per user, per key, right? So there will be, for one key, it will be present in multiple chunks. And once we create the chunk 3, which is the compaction of both these chunks, obviously this would be lesser space than 200 MB and we can get rid of this. So we are obviously doing a good job and saving space over here. So there was a cost that we incurred while doing the append only strategy, and that cost we will get we will get rid of it now. What this compaction looks like, well, let's say there is some key user 5 and the value for there is 33. However, in let's say chunk 2, user 5 is having value 71, and also there can be 20 more updates for user 5 over here. Similarly, 20 more updates for user 5 over here. We pick, when we are doing the merging, this was 33 that we picked. Over here we take 71 and this is the final value. So this is how it's going to look like. The chunk 3 will have its own key value lookup storage. And once we update user 5 with 71, whatever the byte offset was for this file, we store that in our key and byte offset, right? So for user 5, we store what is the byte offset over here, and so we have the chunk, we have the data in it, and we also have the updated hash map. So this is the compaction process, which will give us this beautiful way of handling the extra disk space that we were using. So as I've discussed, now we can reroute the reads to chunk 3, and now we can delete the chunk 1 and chunk 2, and this is how it looks like. What else? I think we have not yet covered about the recovery. Now let's say when you are doing everything is working fine, but there is a power failure. Now what? This is still simple because everything is being persisted to disk. We can go through all the chunks and the active file. We can build their hash maps and we are back. We can again do writes, we can again do reads, right? Super easy recovery, but it might be a bit slow to go through all the chunks, and that we can, like, basically going through all chunks, creating hash maps, it might take time. Even better thing is if we also store these hash maps, right? Chunks are only immutable, and this is where now we are getting that beautiful benefit of immutability. Since chunks are always read only, once chunk is created, it will never be modified. Never be modified. Even if we have updates on the keys present in the chunks, they are going to be present in a new file, not that one. So since they are immutable, we can also persist their hash maps to disk because they are also not going to change. So we don't need to scan the entire file to build this. We already have stored that in the disk, and this can even speed up the recovery process. Now I believe you can see the benefit of immutability. Finally, there are still few caveats. As a candidate, you should definitely talk about scenarios. It shows that you are aware about things. You can say that we are still not decided how we are going to handle deletion of keys, right? Also, the file format right now, it's CSV, just because it's easy and readable, but you can get better optimizations if you store data in binary. You can, in binary, what happens is in the file, it's not human readable, but it will be written in binary format. And generally what people do is they say that, okay, the length is of, let's say, 10 bytes and for the key. So next 10 bytes will be for the key, and then you can say for the value there are 20 bytes and the next 20 bytes are for the value, something like that. So everything is encoded in byte format, in which you have certain you store certain information about how to read the value in that byte format. Okay, so that gives us better performance. Also, what about the concurrency control? That in this case, it's super easy because there will be always one writer who is going to do the append. There can be multiple readers who can do read at the same time, because of immutability, we don't really care about such scenarios. So it's super easy. Again, lastly, there are number of keys. If they increase quite a lot, well, this is something which can be a bit of a problem, because in our case, since we are having hash maps which are there in RAM, in memory, so the number of keys, they should definitely fit in RAM. This is one limitation that I like. At this point of time, it's already 45 minutes or something that have elapsed in the interview, and you can simply say that this is something which we do not support, right? Having these discussions saying that we do not currently support this just shows that you are a professional software developer who knows about systems, who knows what can go wrong, who knows what we have covered, and all those things really impress people quite a lot. Also, lastly, you can say that if you want to perform range queries, that I want to go through the bank statements of user 33 to user 99, well, we do not provide something, we do not have any optimizations for range queries. It's something that B-trees do provide us. The scanning from nearby keys is quite easy in that case. So yeah, these are some things I wanted to discuss. I hope you had a great time and you learned quite a lot, and you saw that there are so many things that go behind the scenes in doing something as a key value storage with append-only strategy. So I hope you had fun. Again, for all the videos that we have done so far, go through the system design series that we have started. I hope you really enjoy this, and it gives you a better idea of how to actually talk about system design in interviews. And let me know in comments if you like this, share this with your friends, and definitely press the like and subscribe button and also the bell icon so that you do not miss any updates from me. Thanks guys, I'll see you in the next one.